The topic of my presentation is a survey on federated learning towards privacy preserving AI, and this was under the supervision of Professor Wolfgang Maas. And the contents today that I would like to discuss is federated learning and what are the different terms to know, and federated learning life cycle, its training process, along with what are the different classification of federated learning and various privacy techniques. And then we go to implementation frameworks. And I would also like to discuss how federated learning is applied in industries, and then finally conclude and give insights on future research. So coming to federated learning. So this is a new term which is being heard over the recent times, and it is a machine learning setting where you have many clients, and they collaboratively train a shared model and under a server, and the data is here decentralized, which means uh, before we used to have the data which is stored on the server itself, but now we have decentralization of data. So here we can refer the federated learning term as um, machine learning, where you have decentralization of data. So the main advantage of federated learning is like the data is now moved to edge devices. Here, edge devices may be like your mobile phones or your iPads or etc. So this way, it improves the latency, and you can also work offline, and we have a better battery life because the training happens when the device is ideal or when it's not in use by the user. And you also have privacy advantages as the model is trained on the device itself, so the server has no information about the data. And we have various terms like machine learning, distributed machine learning, federated learning, centralized federated learning, decentralized federated learning, and peer-to-peer or fully decentralized learning. So we need to know each of these terms before we get into federated learning in detail. So coming to distributed machine learning. So the main aim of distributed machine learning is that the data here is distributed onto multiple computing nodes, which means it aims at parallelization of computing power uh, by distribution of data or models. So here we have like data parallel or model parallel methods. So still we have some open issues in distributed machine learning, like performance issues, fault tolerance. Suppose you have one of the computing nodes which doesn't it is off or something like that. And then we also have some privacy issues, and such a model is not portable, so we have portability issues also. And coming to fully decentralized or peer-to-peer learning, here we have a peer-to-peer topology, which can be seen as a dynamic connectivity graph, where each client in the peer-to-peer topology communicates with other client in the dynamic connectivity graph setting, and it doesn't have any central orchestration like server. And then we have decentralized federated learning. By the term decentralized, you might know like the data here is distributed onto different nodes and is not it doesn't have any central authority like server. So the computing nodes here, they communicate between themselves in order to compute the shared global model, and the model updates are then sent to the server without any. So this process happens without any coordination or like the central authority, which is called as a server in general terms. And then we have centralized federated learning, where you have a clear setting of a central server and you have multiple clients which communicate between themselves under the orchestration of central server. And the number of clients which have to participate in this federated learning are selected by the central server, and everything happens under the control of server. So here we have a bottleneck, like if the server might fail, or there are some reliability issues, then it would be a bottleneck to the entire federated learning setting. And then coming to federated learning life cycle, you can see we have like multiple clients. Here we refer to as edge devices like mobile phones or iPads or something like that. And then you have a central server which coordinates with the clients. And then you have this model testing, which is done by the engineer and analyst. And then it's finally the global model is then shared to the different end users, which is like deployment. And I would discuss like each of the stages of life cycle of federated learning. So the life cycle is divided into like 6 stages. So first we have like problem identification. In problem identification, so the model engineer first he has to identify what is the problem we are trying to solve with federated learning. And then in client instrumentation, which is the second stage, the data is stored on each client locally, because this is a federated learning setting. So the data is stored on the client devices. And then sometimes we might have like different additional data. For example, in a supervised setting, we might have the labels of the data, training data. So this is also stored in client instrumentation stage. And then we go to simulation prototyping, which is stage 3. And then here the model architectures are prototyped. And suppose like in this federated learning setting, we test the learning hyperparameters using the federated learning simulation, and it is carried out on a proxy data set, like we have MNIST data set and so on. And the simulation prototyping stage is an optional. And then coming to the next stage, which is federated model training. Here we train the federated model using various optimization techniques and so on. And then once we have the trained model, then we go to federated model evaluation. So in this evaluation, we need to evaluate the various like the federated learning model, and then we need to select one of the best models. And then it depends on what are the various metrics that we take into account in this stage. And the evaluation is carried out on each client. And then the final focused updates, model updates are then sent to the server. And then finally we have the deployment, where once you select one of the best models, then you deploy it to the entire world, which means like the application owner, he launches the model, and the end users are now ready for the model to use. And then now we discuss the stage 4, which is like federated model training in detail. So it is further divided into 5 stages, where we have like a client selection. So here on the right hand side, you could see a diagram which is popular from Google, which describes how federated learning training process happens. So here you have various mobile devices, and this is a global model which is sent to the sent from the server to different clients, which are mobile devices. And then the model is now trained on the user uh, device itself based on his actions. So the model training happens here. And then finally, we do not share the model to the uh, server, but we send only the focus update, which is the weight update. We just send the weight updates to the server. So these are the different weight updates from each client. And then finally, the server, when it receives all the weight updates, it just uses federated averaging mechanism, where it aggregates all the weight updates, and then it trains its own model, and finally gets the updated global model, and then it sends this global model to the client devices again. And this happens in an iterative process until we have a good global model. So this is what is meant by federated learning training process. Yeah. And then based on how the data is distributed across various client devices, the federated learning can be divided into like 3 different categories, which is like horizontal federated learning and vertical federated learning, and we also have like federated transfer learning. Coming to horizontal federated learning, as you can see from the diagram, we have various samples like from different organizations here. So this is data from company A and data from company B. So we use horizontal federated learning, where the data which is used for training the data sets, they have like same feature space, but they differ in sample space. And then suppose, for example, you can understand this scenario by taking like you have like 2 different banks. So the banks, they have like same features, like the feature space for the banks is the same because they run under the same they carry out the same work, but the sample space, which means the users which who have accounts in the banks, they are different. So this is one of the example for horizontal federated learning. And then uh, this is how horizontal federated learning architecture look like. So here, if you see in the diagram, you have like various databases, and then first, like the parties, like the clients, they train they train the model based on their own data. So this is what happens in the first stage. And here, once they train the model, they encrypt their gradients, and then they send the encrypted gradients to the server, and then the server collects all the gradients from each of these clients, and then it then performs secure aggregation. There are various techniques to perform secure aggregation, and then once it has final aggregated model, then it sends back the model updates back to each of these clients. And then once they have the updated model gradients, they update their own model, and finally they have the global updated model on each of these clients. And coming to vertical federated learning, here we have like various like data from corporation A and B, and then it is used in cases where the data sets share same sample ID space, but they differ in the speech feature space. So suppose you have a bank and also a e-commerce company in the same city, then you might have like the samples, like the users of the same city might have a account in a bank and also in an e-commerce company, but the feature space differs because they are 2 different sectors. So the federated learning system here, like it consists of like 2 different parts. First is like encrypted LTT alignment, and then encrypted model training. So the basic idea of this encrypted entity alignment is to select the common users. So we have like company A and company B. So here we select the standard users of both companies, and then once you have the common entities, then we use these entities data to train the machine learning model in the encrypted model training. And this is the architecture of vertical federated learning. So here you have a third party like a collaborator, and in the first stage, he creates encryption pairs and sends the public keys to both the corporations like A and B. And then now both A and B, they exchange the intermediate results for calculation of the loss and also like gradients. And then now both the companies, they compute the encrypted gradients and they send the encrypted gradients uh, back to the collaborator C. And then now the collaborator C would now decrypt the gradients and the loss, and then he would send them back to both the corporation uh, and update the model parameters like accordingly. So this is which happens in vertical federated learning. And coming to federated transfer learning, it is used in cases where we have like uh, both various sample and also in feature space. And you have the data from corporation A, and model is trained on this data A. And then we use the same model to train on data from corporation B. This is what happens in like federated transfer learning. And coming to federated learning privacy mechanisms, we have various techniques in order to ensure privacy. Um, as you can see, like in this federated learning setting, we have a server which has no information about the client data, thus preserving the privacy. So here we have like secure multi-part communication, and you have like various clients and they communicate with each other such that they do not have any information about each other client. Here they refer to as party, and it means like they have like zero knowledge about the participating client or maybe the party. So this is what is meant by secure multi-party computation. And then when coming to homomorphic encryption, here it uses like various mathematical operations like you see like ciphertext and other things like encryption mechanisms so that the data privacy of the user is protected and the parameters are exchanged without any loss of privacy. And like here the main thing is like uh, we have various mathematical operations, which means like uh, we need to be careful uh, like how this mathematical operations would be performed, and uh, how we could there are other techniques where we could also decrypt these things. So it follows like we do not have any pre or decryption before performing the homomorphic encryption. And then coming to secure aggregations, here we have like multiple clients and a server. So here each client it will submit a tensor value, and then a server just collects all these client values, and then it aggregates to a common sum. And then the server here has no information about the client data except for the computed value. And then we have secure shuffling, which is similar to the secure aggregation, but values here are like multiple set, like multi-set singletons. And it like based on various implementations, it we could use various like combination of secure shuffling and secure aggregation. And coming to secure boost, and it uses a secure boost like a gradient boosting algorithm, and it consists of like two steps. And in the first step, it aligns the data based on a privacy constraint, and then in the second step, it learns how to provide security over multi-parties, keeping the training data secured. And then coming to private information retrieval, here we have like one client and one server, and the client would download the model from the server, and the server the client has to ensure that the server has no information about the client entry, which it like the client data. And here this procedure is highly expensive. And coming to differential privacy, we have three different categories. Like one is local differential privacy, which means like each client he applies this differential privacy transformation before sending the data to the server. Here, the data means like the model update to the server. And in case of differential distributed privacy, here the clients first compute a focused report, and then they send these encoded reports to the server. So as the computed this focus reports already satisfies this differential privacy requirements. In this way, it enables the security of the federated learning system. And coming to hybrid differential privacy, it combines both the techniques uh, based on two different like trust models. One is like most trusting model, and the other is like least trusting model. And in order to implement federated learning, uh, we have various frameworks such as TensorFlow Federated, PySwift, and Parallel Federated Learning, Leaf, and Clara training frameworks. And the most popular ones are TensorFlow Federated and PySwift. So coming to TensorFlow Federated, it was developed by Google, and it has like two different parts, like modules. One is Federated Learning API, and here we could use this API in order to implement a federated learning simulation by using the existing like models and the data. And coming to Federated Core API, here we can build new federated learning algorithms. And we have PySwift, which is another federated learning implementation framework, and it is also open source, and it was developed by Open Mind community, and it is it is an extension to known deep learning libraries like PyTorch, Keras, and TensorFlow, which makes it very easy to learn the PySwift framework. And then coming to application of federated learning in industries. So deploying federated learning in industries is very difficult, as the industries have heterogeneous like working conditions, and uh, the the machines there are have various reconfiguration configuration parameters. So it is difficult to deploy them in industries. And the machines should be highly available, and the reconfiguration of each machine, it is crucial for the competitive product pricing in industries. And if we apply federated learning in industries, then it would lead to better resource optimization of edge devices, or maybe the machinery in the industries. And it prevents negative knowledge transfer, and it is used for detecting anomalies before like the early in production. And it is used for resilience management and optimization in industries. And then we have like the character, it can also be referred as challenges, or maybe the main characteristics of federated learning, which means it's IID, which is non independent and identically distributed data. So in case of this mobile device setting, where you have like multiple mobiles, each user generates like different data. So the data generated from one user is different from data which is generated by other user. So here it can be referred as non-IID data. And as we have like multiple clients which participate in federated learning process, some of the users produce like more data than others, which makes it unbalanced system. And then coming to massively distributed, so we have like more mobile devices than the training samples on each device, which makes it like massively distributed like system. And then we as we have in mobile connections like unreliable or unstable and asymmetric mobile network connections, then the communication between the client and server becomes very limited, so it's referred to as limited communication system. These pose as challenges for implementing the federated learning. And then finally, uh, we could conclude like federated learning would thus provide a platform for the industries, like for many enterprises, to build a common like cross enterprise and cross data ecosystem, like ecosphere for AI and machine learning. And companies are now using federated learning mainly in production because they want to communicate and collaborate with each other in order to build a global shared model, and also ensuring based on the privacy mechanism. And then federated learning, in future, like federated learning would really break the barriers between both between the industries. And then it would establish a new community where the knowledge and the data between the industries could be shared securely. And then the yeah so the need for AI would be brought to every corner of the life using federated learning. And as of now, the federated learning research is still in progress. Like research is happening tremendously, but it is in a like a early stage. In the near future, we could see like in industries, or maybe even now, like when we use mobile devices, we have this federated learning. As you can see, like Google is already implementing federated learning for the keyboard, like Gboard, which they have. And also Apple is using federated learning for Siri, and so on. And finally, these are a few of the references. And yeah, thank you so much for your attention.